Hello, I am Václav Novotný and welcome to the tutorial of energy sources and conversions. This tutorial will be focused on internal combustion engines. That means Otto, diesel and mixed thermodynamic cycles. So let's see how the internal combustion engines work. Internal combustion engine is typically a piston engine, where we have here illustrated a cylinder with the inlet valve and inlet piping, outlet valve and outlet piping. Here we have the bore of the cylinder in which we have some piston. So for the starting point, let's say that we have mixture of air and fuel inside of the cylinder enclosed by the piston, and the piston is moving up. That means compressing the fluid, compressing the air. The valves are closed. Let's call this point number 1, and let's draw it in the PV diagram of this cycle, of this system, pressure and volume, where the starting point would be, let's say, somewhere here, point 1. Then as the piston is moving up, so in ideal case isentropic compression takes place. So the piston compresses the working fluid, the gas, into the point 2, which we will call top dead state or top dead center. The piston compresses the working fluid into the state 2. The compression is ideally isentropic. So in PV diagram it will look somewhat like this, to the point 2. Then at this point ignition takes place and the fuel ignites, and suddenly the temperature and pressure in the chamber of the cylinder and the piston, in which is the working fluid, will increase. This process is very quick, so it will not be just point 2, but also we can say that the point 3 will be approximately at this position of the piston. So we have rapid increase of the pressure and temperature to the point 3, and then the piston will be moving downwards. The expansion will take place to the point number 4, illustrated over here. The expansion will produce some work, and in the PV diagram the expansion will look somewhat like this. Then, at point number 4, there will start the so-called exhaust stroke, where this valve over here will open, and the working fluid, which is now flue gas, will be exhausted outside of the cylinder area. So here we had point number 4 in the PV diagram, and now the piston will always move upwards. And in the PV diagram we have isochoric exhaust, because the gas itself. Now we have isochoric heat rejection, because the gas itself is first moving outside at constant volume of the chamber. So it looks somewhat like this. And as the piston gets from the bottom dead center again to the top dead center, so it removes almost all, ideally all, of the working fluid from the cylinder. So let's call this point number 5. It would be somewhere here. And in this real cycle, still during the exhaust stroke, the pressure will be a little bit above the ambient pressure, and then after the point 5, the piston will start moving downwards. The intake valve opens and it will start to suck in the mixture of the air and the fuel, and as it sucks this mixture, so the pressure is a little bit lower than ambient, which we have illustrated over here. And we are getting back to the point 1. The piston is at the bottom dead center, ready for the compression stroke with the mixture of combustion air and fuel in the volume of the cylinder. This was the illustration how the real cycle works. In order to calculate the performance of the cycle, we however are using simplified cycles, which are so-called comparative cycles, which contain the clearly defined thermodynamic changes. So for that, we again start with the cylinder, with the working fluid inside and at the ambient pressure. So that was our point number 1. And the cylinder is moving up to the point where the working fluid is compressed. To the point number 2. And now let's illustrate this comparison cycle with the green color. So here we have point number 1, here we have point number 2. This compression is very fast. There is no heat transfer to the surroundings, no heat generated, no combustion takes place. So it's adiabatic change, and the ideal adiabatic change is isentropic change. So from point number 1 to point number 2, we are having an isentrope. Now the piston is at the top dead center, and as we said before, at that position stays basically between points 2 and 3, where the heat addition takes place. As this is a constant volume, so the heat addition as ideal change is isochoric change. So constant volume change from point 2 to point number 3. And in the working fluid takes place combustion, which basically means that heat is supplied into the working fluid. Now we have the high pressure, high temperature working fluid at point number 3, which acts by force to the cylinder. The cylinder moves downwards, the working fluid expands to the point number 4. This expansion process, again, there is no heat transfer. Ideally there is no heat transfer with the surroundings. So it's adiabatic process, and the ideal adiabatic process, or a reverse adiabatic process, is isentropic process. So we are having isentropic expansion from point 3 to point number 4. And then in this comparative cycle, so the piston stays at the bottom dead center, and change from point 4 to point number 1 is isochoric, volume is constant, while the heat is rejected. So here we have heat output. So this was the heat. And then for the work, as I said, point 1 to 2 is compression. So we need to put in some compression work. And then process 3 to 4 is expansion, where the work is produced. So we are having the expansion work. Now let's also have a look how this cycle works in the temperature entropy diagram. So we had point number 1 at the point of low temperature, at the air intake. Then we are having isentropic compression to the point number 2. Following is isochoric heat addition. In the TS diagram it looks similar to isobaric heat addition, just it's a little bit different slope of the curve. To point number 3. Following is Isentropic Expansion, where the work is produced to the point number 4, and then Isochoric heat rejection back to point number 1. And this cycle is called Otto Cycle. This cycle very well models the spark ignition engines. If we have compression ignition engines, so the process 2 to 3 is not that fast, and it's often modeled as Isobaric process. So then the process from point number 2 to point number 3 would look somewhat like this. And as you can see, the point number 3 is at lower pressures. It will be also at lower temperatures. The isobaric process looks somewhat like this. Here would be the point number 3, and from the point number 3 would take place the expansion to point number 4. Now it looks that this cycle would have lower efficiency because it has lower volume in the TS diagram. In real applications, however, these cycles have higher compression ratio. Therefore, actually the real efficiency might be slightly higher. The real behavior of the process between here points 2 and 3 might be also something between this. Let's say it would look like this, with the point 3 over here. And then this process would be modeled as a combination of Isochoric and Isobaric process, let's say with some point X in the middle. And in the TS diagram it would be partly Isochoric to the point X, and then Isobaric to the point 3. So the green one is Otto cycle, the purple one is diesel cycle, and the blue one is called mixed cycle, or sometimes also dual cycle, or Sabates cycle. Of course, here I was drawing the real behavior in the PV diagram. If we would draw the clearly defined thermodynamic changes that we calculate with, so the purple one would be isobaric heat addition, straight line. The Otto cycle we had here is isochoric change, and the blue one would be part of the vertical isochoric to the point X, and then part of the isobaric horizontal to the point 3. Now just note one thing: when we want to have the ideal cycle, in this case the ideal Otto cycle describing the red cycle over here, so here from the point number 2 we would go with the isochoric change at constant volume up, and then from the point 2 the isentropic expansion would look somewhat like this. And we can see that actually the intersection of these two curves is up over here at much higher pressures and also eventually higher temperatures. So this triangular area is a result of the real system with the piston with real kinematics and time of the changes, while the ideal cycle goes up here up to this point. In our calculation, we will start with example of the Otto cycle. So we will consider ideal Otto cycle with compression ratio of 7, which uses ambient air at 100 kilopascals and 15 degrees C. The heat addition is 900 kilojoules per kilogram, and we will assume that the working fluid is ideal gas with constant specific heat capacity, with given isentropic exponent and ideal gas constant R. Alright, so we are having the Otto cycle, and our input parameters were the isentropic exponent kappa being 1.4. Then the specific heat capacity Cp being 1005 kilojoules per kilogram at Kelvin. The heat input is 900 kilojoules per kilogram, and also for the air or for our working fluid the constant R is 287 kilojoules per kilogram and Kelvin. And finally, the volumetric ratio of the cycle was set as 7. So here we will have a table of the nodes of our cycle. So we will have the node 1, 2, 3 and 4. As we have the cycle in the PV diagram, where in the PV we start somewhere with the point 1, then follows the isentropic compression to 2, isochoric heat addition to point number 3, isentropic expansion to point 4, and isochoric heat rejection to point number 1. Similarly, in the TS diagram, we are having the point 1, then the point 2 after isentropic compression, heat addition to the point 3, isentropic expansion to point 4, and isochoric heat rejection back to point 1. So here the entropy is constant, here the entropy is constant, here the volumes are constant. This, which means constant volume is over here, and here are the changes of constant entropy. Okay, so we have the nodes, then we will have pressure, temperature and volume, with the basic units pressure in pascals, temperature in kelvins, and unit volume in cubic meters per kilogram. Now what do we know for the beginning, for the start? So at the point number 1, we know the pressure. It was also one of the input parameters here. The ambient pressure, which was 100 kilopascals. So the pressure at point 1 is 100,000, which is the pressure of the ambient. The temperature at point 1 is the temperature of the ambient, which we had also specified. Temperature ambient was 15 degrees C. Which is 288.15 kelvins. Now during the calculation, we will use at first the ideal gas equation, which is PV equals RT, and from that we can get the pressure at the point 1, where the pressure is RT over P. The pressure is RT over V, and the volume is RT over P. So the volume is RT over P, 287 kilojoules per kilogram Kelvin, temperature 288 degrees Kelvin, divided by the 100,000, the pressure. And the volume at the point 1 should be therefore 0.827 cubic meters per kilogram. Now with the point 2, we know the compression ratio. That's the ratio of volumes, the volume 2 and volume 1. So the volume at the point 2 is volume at the point 1 divided by the volumetric ratio, the compression ratio. So it's the value over here divided by 7, and we get 0.118 cubic meters per kilogram. Now, because the change 1 to 2 is isentropic change, so we can use equation of isentrope to get the pressure and temperature. So from the ideal gas equation, we will get that P1 V1 over T1 needs to be valid also. This needs to be valid also for any other point, so the same needs to be valid for P2, V2 and T2. And the equation of the isentrope is PV to kappa is constant. Therefore, it needs to be valid that P1 V1 to kappa is also P2 V2 to kappa. Now, because we were calculating with the volume and we want to get the pressure, so we can actually use directly this equation, and we can get that the P1 over P2, or maybe let's put it the other way, P2 over P1 equals, now fraction V1 over V2 whole member to the isentropic exponent kappa. So we can write that the pressure P2 is pressure P1 multiplied by this in here. So the pressure at point 2 is pressure at point 1 multiplied by the ratio of V1 over V2, which is actually the volumetric ratio, to kappa. Now the pressure one is 100,000, volumetric ratio is 7, kappa is 1.4, and we will get that the pressure at point 2 is 1,524,534 pascals, so about 1.5 megapascals. Now the last thing at the point we are missing is the temperature at the point number 2, and for that we can use the ideal gas equation. So the temperature is the last thing we have not yet expressed here. So the temperature is PV divided by R, like this. So in here the temperature is P2 V2 divided by R, pressure over here, volume over here, and the specific gas constant 287 kilojoules per kilogram Kelvin. So the temperature at the point number 2 is 627.56 kelvins. Now the change from 2 to 3 is change at the constant volume. So the unit volume at the point 3 is same as unit volume at the point 2, which means 0.118, and it's the process with heat addition. So since it's at constant volume, then we can write that the heat input, or generally heat transfer, Q, is specific heat capacity at constant volume, which is CV times delta T. And now the specific heat capacity can be obtained basically for the ideal gas in two ways, two methods. One is based on the fact that the isentropic exponent, kappa, is the so-called ratio of specific heats. That means it's Cp over Cv. And therefore the Cv could be obtained as should be Cp over Cv. So Cv could be obtained as Cp divided by kappa. The second method to get the specific heat capacity at constant volume is to subtract the ideal gas specific ideal gas constant from the Cp, so it would be Cp minus R. In our case, the first method, it would be 1005 divided by 1.4, and it will get a value of 717.85 kilojoules per kilogram and Kelvin. While if we use the second method, Cp minus R, so it's 1005 minus 287, and it results as 718 kilojoules per kilogram and Kelvin. So we can see a small discrepancy over here between the value here and here. The reason for that is in rounding of the numbers such as the specific heat capacity or the specific gas constant. For further calculation, we will be using the first one, 717.85 kilojoules per kilogram and Kelvin. So now the temperature at point 3 can be obtained as temperature at point 2 plus the temperature difference, which is the added heat, Q in, divided by the specific heat capacity at constant volume, CV. So the temperature T2 plus 900 kilojoules per kilogram, that means 900,000 joules per kilogram, divided by CV, which was 717.85 joules per kilogram, and we get the temperature at the point 3 to be 1881.3 kelvins. And now we have the volume, we have the temperature, so the thermodynamic state is clearly defined and given, and using the ideal gas equation we get the pressure at the point 3, where the pressure is RT over V. So 287 times 1881 divided by the 0.118, and it returns the result to be the pressure at the point 3, 4,570,212 pascals, so about 4.5 megapascals. What follows now is the isentropic expansion from point 3 to the point 4 over here. So now the change 3 to 4, or the node number 4, where for the node number 4 we know the unit volume, because between points 4 and 1 is isochoric process, so the volume needs to be same as with the point 1, which was 0.1 0.827 cubic meters per kilogram. Now for the pressure at the point 4, so we will again use the equation of the isentrope. PV to kappa equals PV to kappa is constant, so we will use this just with the pressures at point 3 and 4. So P3 V3 to kappa is P4 V4 to kappa, and now we can write that the pressure P4 over pressure P3 is volume V3 over V4 to kappa, and then pressure P4 will be pressure P3 multiplied by this over here. And the V3 over V4 is actually 1 over the volumetric ratio. So the pressure at P4 is pressure at P3 multiplied by 1 over volumetric ratio to kappa. Pressure 4.5 megapascals, 4,570,000 times 1 over 7 to kappa 1.4, and we will get that the pressure at the point 4 is almost 3 atmospheres, 299,778 pascals. And now we have pressure, volume, and we can get the temperature same as here in the point 2. So the temperature at the point 4 will be P4 times V4 times 1 over R, the specific gas constant, which results that the temperature is 863.81 kelvins. Now let's have a look at the work, heat and the efficiency of the system. So let's put in work over here, heat over here, heat transfer, and we will have the change 1 to 2, 2 to 3, 3 to 4, and 4 to 1. So now the change 1 to 2, it's isentropic change, so the heat transfer is 0. And the work is, as it's isentrope, so also we calculated it last time with the Brighton cycle. The work is Cp delta T. And if we use the standard thermodynamic notation, so the result would be minus 341 kilojoules per kilogram. Both work and heat will have units kilojoules per kilogram. Those are unit work and unit heat. So minus 341.11. Now the change 2 to 3 is the change at the constant volume. The heat transfer is the heat addition we have over here. With the standard thermodynamic notation, it's heat input into the system, so it would be positive value of 900 kilojoules per kilogram. And for the work at the constant volume, the work or the technical work, we define it typically as VdP. Now the volume is constant, so it's V times delta P. You can see that the volume 2 to 3 is the same, the difference in pressures over here, and we will get minus 359.8 kilojoules per kilogram. Now points 3 to 4, isentropic expansion, so again the heat transfer is 0, and the technical work Cp delta T, which will now get 1022.57 kilojoules per kilogram. And finally the heat rejection for points 4 to 1. So the work VdP, V delta P, which will yield 165.2 kilojoules per kilogram, and the heat rejection, so it's Cv delta T, the Cv we derived as 717.86 joules per kilogram and Kelvin. Temperature difference between points 4 and 1, and the resulting value should be 413.24 kilojoules per kilogram. Now we will calculate the efficiency of the cycle, where the efficiency of the cycle can be written as net work output, or just one work of the cycle, divided by the heat input into the cycle, where for the work output of the cycle we take the sum of these, because in each change we have here we can see that there is some work performed. The work of the cycle, or the sum of the works in each changes, is 486.86 kilojoules per kilogram, and the heat input into the cycle is over here. And just one thing, here should have been the negative sign, because this is the heat rejection is out of the system, so therefore negative. There is positive. So the work of the cycle, 486.9 divided by 900 will get us 54.095%. We can also calculate the efficiency of the cycle as the heat input minus heat output divided by the heat input. It is based on the balance assumption that there is only the work and heat output and input that we calculated over here. So the heat input minus heat output should actually be the same as the work of the cycle. If we perform this calculation, so we will however get very slightly different value, which is 54.084%. And the discrepancy between these two over here is basically based on the same reason as was the discrepancy between the specific heat capacity at constant volume when we calculated it from the kappa and from the specific gas constant, because there were some rounding errors. Okay, so this was the example calculation of the Otto cycle. The second example will be a turbocharged diesel cycle. Let's consider ideal diesel cycle with compression ratio of 12, where because of the turbocharging, the intake air is at 200 kilopascals and 130 degrees C after the compressor. The heat addition is 1650 kilojoules per kilogram, and the fuel has lower heating value of 42 megajoules per kilogram. Then we also have the dimensions of the engine, with the bore diameter being 0.8 meters, and the stroke of the piston will be 1.2 meters. And this engine, you can see that it's really rather large dimension engine, so these engines are typically running at low speed, which here will be 100 RPM, 100 rotations per minute. We will assume again ideal air as the working fluid, with the constant specific heat capacity, with the given isentropic exponent kappa, and here with the given molar weight of the air, 28.97 kilograms per kilomole. And the task in this example is to calculate the cycle efficiency, compare the performance with manufacturer's power consumption ratio, which is given as 171 grams of fuel consumed per 1 kilowatt hour of power produced. And also we will calculate what would be the power output per one cylinder of this rather large diesel engine. So first, let's draw a scheme how this system works. Because it's turbocharged engine, so we are having intake air. Here we have some ambient, where the air goes into the compressor. At the outlet of the compressor, the air goes into the engine itself. we have the intake and outlet port. So here we have the engine itself. Then at the outlet of the engine, it still needs to go into the turbocharger and to the outlet. We will assume that the pressure at the intake will be same as the pressure at the outlet. And for this turbocharger, so it is a compressor directly connected with the turbine, and the turbine power output is just enough for the compressor power requirement to compress the air. So there is basically no work from this system, and the only thing that it makes is that it increases the pressure of the air at the inlet of the engine, but also at the outlet of the engine we need to have pressure sufficiently large to run the turbine. Before we start calculating the diesel engine, let's draw illustrative PV and TS diagrams so that we know what we are calculating. So we start again at some point 1. Where we have the isentropic compression, some point number 2. Then in the diesel cycle, the heat addition is isobaric, so 2 to 3 is isobar. Then isentropic expansion to the point number 4, and isochoric expansion vertical line down to the point number 1. In the TS diagram, from the point 1 we start with the isentropic compression, then isobaric heat addition, where the isobar is not that steep as the isochor. Then we have the expansion, so here we had point 2, 3, expansion to the point number 4, and then isochoric heat rejection, where the isochor is steeper than the isobar. Perhaps I should do it. Now it should be more illustrative that the isochor is steeper than the isobar. And we have heat input over here, and heat output over here. And in the PV diagram, heat input is in here, and heat output is in here. Okay, now what we had given as the boundary conditions, it was the compression ratio, which was 12. Then we had the parameters at the inlet, which are parameters at the point 1. Kilopascals, which we said also it will be the point 1 at the outtake, that the we said that the cycle is ideal, that means closed cycle. In the real cycle, or in the real system with the turbocharger, you could have the situation where this outlet pressure would not be the same as the inlet pressure. That this does not necessarily need to be the same. But in our case, we will consider for simplicity of calculation that it is. So it was pressure at P1, then the temperature at T1 was 130 degrees C, because it's after the turbocharger, so the compressor causes temperature increase. The heat addition 1650 kilojoules per kilogram. Then for the working fluid we had the specific heat capacity. Isentropic exponent kappa. And molar mass of the air as the working fluid, 28.97 kilograms per kilomole. So first, when we have the molar mass, we need to obtain the R, the specific heat, the specific gas constant. So the R is the ratio of capital R, the universal gas constant, and the molar mass. And the universal gas constant is 8.314 kilojoules per kilomole and Kelvin, while the molar mass was 28.97 kilograms per kilomole. And we can see that the kilomoles cancel out, and the R is 0.286. (987) kilojoules per kilogram and Kelvin. Or if we will be calculating in basic SI units, so 286.987 joules per kilogram and Kelvin. Now, in our cycle, let's make a table for each given node. Let's make a table for parameter at each node. So we have nodes 1, 2, 3, and 4. And we will have pressure in pascals, temperatures in Kelvin, and unit volume in cubic meters per kilogram. So in the problem statement was given that in the point 1 the pressure is 200,000 pascals. The temperature at the point 1 was 130 degrees C, which is 303.15 kelvins. And the volume at the point 1 can be obtained from the ideal gas equation, where it will be the RT over P. Now we calculated the R over here, temperature 303.15 divided by 200,000, and we get the unit volume to be 0.435, pretty exactly 0.435 cubic meters per kilogram. Now going to the point 2, we will start with the unit volume, where we will again use the volumetric ratio. So the volume at point 2 is volume at point 1 divided by the volumetric ratio. So 0.435 divided by 12, which is 0.036 25 cubic meters per kilogram. Now we can use the equation of the isentropic change to get the pressure and temperature. Last time we used directly the volumetric ratio, that the pressure times volumetric ratio to kappa is that the pressure at 1 times volumetric ratio to the kappa was the pressure at point 2. But also we can use the combination of ideal gas equation and the isentrope, and we can, for example, calculate that the temperature at point 2 is temperature at point 1 times V2 over V1 to 1 minus kappa. It's up to you which approach you want to use, but this is just shown so that we see there are multiple options. The resulting value should be, of course, the same. So the temperature at point 2 is 819 kelvins, 819.087. And now we could get the pressure at the point 1 from the temperature and volume. As the R T2 over V2. So the pressure at the point 2 is about 6.5 megapascals. 6,484,000 and 608. Now we have the isobaric heat addition. So since it's isobar, so pressure at the point 3 will be the same as pressure at point 2. Now, because it's isobar, so we will use we can get the temperature change from the heat input and the isobaric and the specific heat capacity at constant pressure. and if we add the temperature change to the temperature at point 2, we get the temperature at point 3. So T2 plus heat input divided by Cp, temperature at the point 2, plus Q in 1650 kilojoules per kilogram, so 1,650,000, divided by 1005 joules per kilogram Kelvin. Or also in the ratio you can use kilojoules over here and kilojoules at the Cp. The temperature at the point 3 should be 2460 0.88 kelvins. The volume can be now obtained from the ideal gas equation, and it would be RT over P. R over here, temperature we just calculated, and divided by pressure, the 6,484,000 pascals. And and the unit volume should be 0.1089 cubic meters per kilogram. Now follows the isentropic expansion, where the pressure at the point 4 can be obtained from the equation of isentrope, as we derived last time, as pressure P3 multiplied by 1 over volumetric ratio to kappa, and this pressure P4 will be 933,026 pascals, 27. Now the volume is the same as the volume at the point 1, because following is the isochoric heat rejection, so 0.4350 cubic meters per kilogram. And finally, the temperature can be either obtained as here from the combination of for basically the temperature equation for the isentropic change, both from the volume or from the pressure as we did last time at Brighton cycle, or we can also get it from the equation of ideal air, where it will be P4 V4 over R, and the temperature at this point at the outlet will be 1414 0.24 kelvins. So we now we calculated the parameters in each node of the cycle, and let's go for the work and heat transfer. So again we will have change 1 to 2, 3, 3 to 4, and 4 to 1. And we will want to get work and heat all in units kilojoules per kilogram. So the isentropic compression has no heat transfer with the surroundings, so the heat transfer is 0, and the work can be obtained as Cp delta T, and the work input will be minus 518.5 kilojoules per kilogram. Now the change 2 to 3, it's isobaric. So since the pressure is the same, so the technical work will not change, it will stay as 0. And we have the heat input of the 1650 kilojoules per kilogram. Now 3 to 4, we have isentropic expansion, again without heat transfer with the surroundings, and the expansion produces work, Cp delta T, which is 1051.9 kilojoules per kilogram. And finally the change 4 to 1, which is isochoric, so the volume is constant. Now the work is V delta P, where the volume is over here, and the pressure change between points 4 and the point 1, and it is 318.9 kilojoules per kilogram. Now the rejected heat can be again obtained, since it's isochoric process, so as Cv times delta T. And we did not specify the Cv at the beginning, so for the Cv we have two methods how to get it. Either as Cp minus R, or also as Cp over kappa. Let's use the second option, and we will get that the Cv equals 717 .86 kilojoules per kilogram and Kelvin. So now we can take the Cv and multiply it by the temperature difference between points 4 and 1. So 1400 degrees C and 300 degrees C. And we will get the rejected heat as 797.6 kilojoules per kilogram. So now just calculate the work of the cycle. Which is sum of the work of each change when we have the proper notation, so we have the negative sign for the compression and positive sign for the expansion where the work is produced. And the work of the cycle should be 852.23 kilojoules per kilogram. So now we can get the efficiency of the cycle, which can be calculated as the work of the cycle divided by the heat input, which would be in this case 51.65%. And also it can be calculated that the work of the cycle is expressed indirectly from the energy balance as heat input minus heat output divided by heat input, and we would get the efficiency 51.66%. Now the values are nearly the same if we take all the valid numbers at the R or the valid numbers at the CV, but still probably in the two valid digits at the molar mass it can cause this slight discrepancy. Now let's have a look at the comparison with the manufacturer's value of the power conversion ratio. Well, let's call it, for example, PCR, power conversion ratio, which was 171 grams of the fuel per 1 kilowatt hour of the produced power. Now what does this actually mean? It's actually somewhat inverse value of the efficiency, because we can also convert the grams of fuel per to heat. So 171 grams of fuel per kilowatt hour. If we multiply it by the lower heating value of the fuel, so multiplied by LHV of the fuel in units, let's say kilojoules per kilogram. So here we have mass, here we have mass, the mass goes away, and then also we need to convert the kilowatt hours to joules or kilojoules. So 1 kilowatt hour is 3600 kilowatt seconds, which is kilojoules. So we can divide it by 3600 kilojoules per kilowatt hour. So here would go kilowatt hour and we will get kilojoules. So it will go like this. Then also the grams need to be converted to kilograms. So 1000 grams per kilogram. And the kilograms also cancel out in here. And we will get the value in kilojoules per kilojoule, kilojoule of the fuel per kilojoule of the power output. So let's calculate this. So we have 171 times the LHV of the fuel was 42 megajoules per kilogram, so 42,000 kilojoules per kilogram divided by 3,600 and 1,000. And we will get 1.995, and now kilojoules of fuel. This was grams of fuel, so basically the fuel just stays here. Do it like this. Fuel state and kilowatt hour of work. So 1.995 kilojoules of fuel per kilojoule of work. And now you can see that also this value is the inverse value of the efficiency. So we can have that the efficiency of the engine, of the internal combustion engine by manufacturer is, well, we can put it as inverse value from what we had over there. So 3,600 times 1,000 over 171 times 42,000, and also the inverse value of 1.995, almost 2, so 1 over 2 is about 0.5. The exact value is 50.12%. So we can see that the manufacturer's value is quite in good agreement with the cycle calculation. So if the parameters are really given in the way that we calculated them, so the smaller discrepancy would be caused by the rounding of the edges of the real cycle, where the real cycle would look somewhat like this, and here would be the exhaust stroke, which would look somewhat like this. And also in the TS diagram, the corners would be rounded based on due to the real. On the other hand, if you compare it with some smaller and high-speed internal combustion engines, so the decrease of the efficiency is not that high, and also it's caused by the fact that it's really just 100 rotations per minute, so the rounding of the edges would not be that intensive. Now let's get the power output per one cylinder. So we had some geometrical parameters as the diameter of the bore, that was 0.8 meters, and the stroke, let's call it L as length, was 1.2 meters. The volume of the working fluid that goes through the engine can be defined as the volume of the cylinder of this diameter and this length. So the volume would be pi times diameter squared divided by 4 multiplied by the length, which is 0.601719 cubic meters, and And we can say that this is the volume of the air sucked into the point 1. The total volume would be this one plus the dead volume, but this is the volume that goes through. So the volume sucked in. And then the mass of this air would be the volume times the unit volume, where we had the unit volume over here, 0.435 cubic meters per kilogram, and the volume at the point 1, 0.6 cubic meters. So we get the mass of this air to be 1.3866 kilograms. Now 1 kilogram of the working fluid of the air makes 852 kilojoules. So the work of this mass will be m1 times work of the cycle, and it is 1181.7 kilojoules. And now the power output in kilowatts would be the work of the cycle multiplied by the frequency, how many times the cycle is performed in 1 second. So it's the work of the cycle multiplied by, and now what is the frequency? We have the RPM, which was 100 rotations per minute. So if we want to get seconds, so we need to divide it by 60. But because this would be definitely 4-stroke engine, so only half of the strokes are working strokes and half of the strokes are intake and exhaust. So also we need to further divide it by 2. So it would be the 1181.7 times 0.83, and we get that the power output per single cylinder of this engine would be 984.77 kilowatts. So you can see that indeed this is pretty huge engine with quite large power output. So that's all for the tutorial for internal combustion engines.